Today, I'm going to introduce our work analyzing the domain shift immunity of deep homography estimation. As we know, homography estimation is a relatively straightforward task for deep learning networks. However, unlike other convolutional tasks, CM-based homography estimation models show a distinctive immunity to domain shift, enabling seamless deployment from one dataset to another without transfer learning. In order to find the source of these remarkable adaptabilities, we introduce a straightforward homography estimation network, the HEN. This network is more sensitive to feature changes compared to some deeper models like ResNet-50. Compared to the model proposed by Deton, our model uses a global average pooling layer instead of fully connected layer as the last layer to provide a better explainability. To minimize potential distributions arising from rich information during focus analysis, we propose the geometric simple shape dataset, the GSS dataset. The images in GSS shares a black background and only contains simple shapes like squares, triangles, and circles. Each item can appear in either outlined or solid form with randomly assigned position and colors. Here is a focus realization on various datasets. The top row is images from common datasets like BSD300 and AFLW2000. The bottom row is images from the GSS dataset. During the training, we follow the traditional training process using synthetic image pairs to train all of the models, and the results are shown in Table 1. We note that all the models showed consistent prediction accuracy across different domains. No matter it's a deeper network like ResNet-50 or very shallow network like our HEN, this indicates that domain shift immunity is not linked to specific network structures. The performance changes between different networks can be easily attributed to their network depths, where a deeper network structure usually have a better performance. However, even the shallowest HEN outperforms the traditional ORB measure by a significant margin, which shows the efficiency of the deep learning-based homography estimation methods. The focus realization results on the GSS dataset here show that the model is focusing more on the low-level texture area instead of the color informations. If deep learning models depend on local texture for accurate homography estimation, images containing more such texture should have improved performance. So we create images with different numbers of items from our GSS dataset and evaluate the performance using the HEN, which is trained on BSD300 dataset. The results are shown in Table 3. We observe that the input images with more shapes have a better performance. This result confirms the critical role played by local texture in homography estimation, as the only difference between these images is the density of local texture. We notice the model demonstrates robust immunity to domain shift when applied to dataset rich in local texture, and they show lower resistance when processing dataset contains lower texture density, such as the GSS dataset. So in order to decode the domain shift immunity, we apply a 3x3 Gaussian kernel to blur various datasets, thereby reducing their local texture. And the performance is shown in Table 4. We observe a decrease of roughly 1.5 pixels in prediction accuracy across all domains after applying the blur. This finding validates the domain shift immunity is primarily attributed to local texture. In this paper, we employed datasets from diverse domains and using various network architecture to validate the domain-shift immunity of deep homography estimation models. Our findings indicate that this immunity remains robust across various underlying network structures. Furthermore, we show the significant dependency of estimation models on local texture for precise homography estimation. Through our investigation, we established a direct correlation between the observed domain-shift immunity in homography estimation networks and their fundamental reliance on their using of local textures.